Hello, in this session we look at this question of June 2017 of the Cameroon GC Board Further Mathematics Paper 3. It has to do with oblique impact. The question says, show that the vectors A equal 3i plus 4j and B equals 4i minus 3j are perpendicular. A smooth sphere A of mass 2m moving on a smooth horizontal floor with velocity 10i plus 5j meter per second impinges obliquely on a smooth stationary sphere B of mass m. At the instant of collision, the line joining the centers of the spheres is parallel to the vector A. Given that the coefficient of restitution between the two spheres is E, and that the direction of motion of sphere A after impact makes an angle alpha with the line of centers, show that A 4 minus 2E times tan alpha equals 3 for 10 marks. B 3 over 4 is less than or equal to tan alpha less than or equal to 3 over 2 for 2 marks. C. Given that tan alpha is less than or equal to 1, find E and hence find the velocity of A and B after impact. That part is for 5 marks. Okay, we start with the first part, proving that A and B are perpendicular. To prove that two vectors are perpendicular, it suffices to prove that their dot product is 0. So A dot B is 3i plus 4j dot 4i minus 3j. That gives 3 times 4, which is 12, plus 4 times negative 3, which is negative 12, and that gives 0. Therefore, A and B are perpendicular. In the next part, we are now given that two spheres A and B of masses 2m and m respectively are colliding along the vector AB. For us to do the analysis, remember, usually when you have impacts, is either there is impact along vector I, along vector J, or along a vector that is inclined. This is along I means the line of centers is horizontal. Along J means the line of centers is vertical, the line of centers or the line of impulse. And when it is now along a given vector, which is neither just in terms of I nor in terms of J, but in terms of both, it means the line of centers is oblique, it's inclined. And when it is inclined, you have to be very careful. So this one is along a vector of the form xi plus yj. And this is the situation we're having. A equals 3i plus 4j. So if two particles have to collide in such a way that their line of centers or their line of impulse acts along this vector, then the first thing we would have to do is to find vector components of the velocities of the various particles along this vector as well as perpendicular to the vector. So take note, since B is perpendicular to A, then we would need to first find the unit vectors in their directions so that we can use them to get the velocity components along and perpendicular to the line of centers. So we start with the unit vector along A. Unit vector along A is supposed to be A cap which is given by 1 over the magnitude of A times A, and we have 1 over the root of 3 squared plus 4 squared into 3i plus 4j. A is 3i plus 4j, so the magnitude is the root of 3 squared plus 4 squared, and that gives us 1 all over 5 into 3i plus 4j. That is the unit vector along the line of centers, because the line of centers is along vector A. So we also need the unit vector perpendicular to A. It's perpendicular to A means it's along B, because B is perpendicular to A. So the unit vector of B is 1 over the magnitude of B times B, and we have again 1 all over the root of B is 4i minus 3j, so 4 squared plus negative 3 squared into the vector 4i minus 3j. Therefore, the unit vector along B, which is the unit vector perpendicular to the line of centers, should be 1 all over 5 into 4i minus 3j. The unit vectors having been found, we are told that A is projected along that line to collide with B, which is stationary. The velocity of A initially is given as 10i plus 5j, and so I would need the component of this velocity along the line of centers as well as perpendicular to the line of centers. So the right component of UA along line of centers should be equal to UA dot A cap. So the vector dot the unit vector in that direction will give the component of the vector along that vector or in that direction, and so I get 10i plus 5j, which is UA dot A cap, which is 1 all over 5 into 3i plus 4j, and that gives 1 all over 5 into 10 times 3, which is 30, plus 5 times 4, which is 20. That gives 30 plus 20 is 50 over 5, which is 10. So that is the component of the velocity of A along the line of centers. We also need component of UA perpendicular to line of centers, and that is given by UA dot the unit vector in that direction, which is simply B cap, because it's perpendicular to the line of centers. That gives 10i plus 5j dot 1 all over 5 into 4i minus 3j, and we have 1 all over 5 into 10 times 4, which is 40, minus 5 times negative 3, which is negative 15. That gives 25 over 5, which is 5. And so essentially what we are trying to do is that the velocity of, we are trying to convert the components of the velocity of A, which were supposed to be we have horizontal component, it is 10i, and the vertical component is 5j. We have succeeded to convert in such a way that they are now in this form. It's like tilting that axis to fit into the line of centers. At this point now we are having but 10A cap in this direction and 5B cap in this direction. So this direction is that of vector 3I plus 4J. So the component of the speed is 10 units in that direction and 5 units perpendicular to that direction. So since we have an inclined line of centers, we have this, and the sphere A is here. It is said to be of mass 2m, and the velocity UA has a component along the line of centers given by 10 units and the one perpendicular to the line of centers given by 5 units. This is A and this is B. B is of mass m and is stationary. So it means the components along 0. The one perpendicular is also 0. This is just before impact. Then at impact we have again 2m and m. We just have a pair of equal but opposite impulses acting on the two spheres. Then after impact we have them separate this way, and this is at impact, and then just after impact. Once we have this is A and this is B. A would take a direction of this form, and again its velocity has two components. We can call it VA. It has a component that is parallel to the line of centers and another component that is perpendicular to the line of centers. The one parallel to the line of centers will change. Remember, each time there is impact, velocity components along the line of centers always change. Initially A was moving along the line of centers with a velocity component of 10. So after impact it would change to a value x that we need to determine. Velocity components perpendicular to the line of centers always remain constant because no impulse acts in that direction. And so the component that is perpendicular to the line of centers before impact, which is 5, would still be inherited at the final position, and so we still have the velocity component after impact perpendicular to the line of centers being 5. For B, the velocity component along the line of centers would change from 0 to a value y, say, to be determined, while the vertical component remains 0 as before. Again, this is because no impulse acts in that direction, that is in the direction perpendicular to the line of centers. So the components of the velocity in that direction will not change. We are told that after impact, the velocity of A makes angle alpha with the line of centers. So this angle alpha is here, angle alpha. So it's the angle actually between the velocity components, or between the velocity after impact and the component parallel to the line of centers, which is x. So This is roughly the diagram that you need in order to do the calculation. In order to do the calculation, then the first thing I would have to do is to find these unknown components of the velocities along the line of centers, which are x and y. To calculate them, just like in any other impact problem, I make use of the conservation of linear momentum as well as Newton's law of restitution. Conservation of linear momentum along line of centers. And so initially the mass of A is 2m and the velocity component along the line of centers is 10. So we have initial velocity or the initial momentum of A being 2m into the component of the velocity in the direction of the line of centers plus m into 0 for B because it is stationary initially. That should be equal to 2m times the velocity component after impact along the line of centers, which is x, plus my, the velocity component of B along the line of centers after impact. And from here we see that 2x plus y should be equal to 20. Call it equation 1. Then Newton's law of restitution, it says that the velocity of separation all over the velocity of approach is always a constant, and that constant is called the coefficient of restitution. It is given in the equation as E. Now for Newton's law of restitution, we take the difference x minus y all over 10 minus 0 equal negative E. That means the velocity components along the line of centers after impact, x minus y in that order, over the velocity vectors along the line of centers before impact, 10 minus 0 in that order. That ratio should give negative E. That is one way of getting that law of restitution. So applying that, we should be talking of x minus y all over 10 minus 0 equal negative E, so that upon cross multiplication we get x minus y equals negative 10E, and that is equation 2. If we take equation 1, 2x plus y equals 20. This is what we obtained from the conservation of linear momentum along the line of centers. We have to solve for x and y, so if I do elimination, I can add so that the y components will disappear and I get 3x equals 20 minus 10E, so that x becomes 20 minus 10E all over 3. So we can say that x equals, you factorize 10, you get 10 over 3 into 2 minus E as the velocity of as the velocity of A along the line of centers after impact. We also need to get the value of y, which is the velocity of B along the line of centers after impact. So we can simply substitute in equation 2. We have that x minus y equals negative 10E, and so y should be x plus 10E, and x is 20 minus 10E all over 3 plus 10E, and that gives 20 minus 10E plus 30E all over 3, which gives 20 plus 20E all over 3. Therefore y equals, factorizing 20, we get 20 all over 3 into 1 plus E as the velocity of B along the line of centers after impact. So having obtained all the necessary ingredients that we need to tackle the question, we can now begin with the A part, which says we should prove that 4 minus 2e tan alpha equals 3. So this is alpha, the angle that A, the velocity of A after impact makes with the line of centers. So this alpha is part of a triangle. Actually, we have that setup. The velocity of A after impact is this way, then the component that is horizontal, then the one that is vertical. So there is a right angle triangle there with alpha this way. The component here is x and the component here is 5. If I can tilt that triangle, I'll have this. So that is actually the setup that is here. This component can still be placed this way. So it is the opposite side of alpha, while x is the adjacent side. So this is the setup. And so we can say that tan alpha equals, because there is tan alpha in the proof, that is why I have to bring tan alpha. Tan alpha should be the opposite, which is 5, all over the adjacent, which is x. And this gives 5 divided by x, and x was given as this. So we have 10 into 2 minus e all over 5. So we see that tan alpha equals 5. Sorry, this is supposed to be all over 3. So division changes to times and we invert, so we get 3 all over 10 into 2 minus e. So we see that 5 cancels to give 2 here, and then we end up with 3 all over 4 minus 2e as tan alpha. When you cross multiply, you then see that 4 minus 2e tan alpha equals 3 as required. In the B part, we are asked to prove that 3 over 4 is less than or equal to tan alpha, which in turn is less than or equal to 3 over 2. So this proof has to make use of the result we have proven in A. So we say from 4 minus 2e tan alpha equals 3. Since tan alpha is involved in the proof, we need to bring in an expression that has tan alpha. And normally, generally in impact problems, when you see an inequality of the form a less than equal a variable less than equal b, you should use the fact that the coefficient of restitution always lies between 0 and 1 inclusive. And so this is where we are going to begin. I would use this and then bring in e in terms of tan alpha so that I work it out to obtain this proof. So we have to say that, but 4 tan alpha, if I expand, minus 2e tan alpha should be equal to 3. My aim is to make e the subject, and so I can send 2e tan alpha the other way and then 3 this way. So I get 4 tan alpha minus 3 should be equal to 2e tan alpha. And my aim is to make E the subject, so I divide through by 2 tan alpha, so I get 4 tan alpha over 2 tan alpha minus 3 all over 2 tan alpha. And so E should be 2 minus 3 all over 2 tan alpha. And so coming back to this, I will now say 0 is less than or equal to E, and E now is 2 minus 3 all over 2 tan alpha less than or equal to 1. So I have this expression in the middle lying between 0 and 1 inclusive. In that expression there is tan alpha. So my aim would now be to simplify that expression until I get the proof. And so it is all about making tan alpha the subject in the middle of the inequality there. I will start by eliminating 2, and to do that I remove 2 on the inequality. Subtracting a constant from both sides of the inequality doesn't affect the inequality, it will still be valid. So 0 minus 2, I get negative 2 less than or equal to negative 3 all over 2 tan alpha less than or equal to 1 minus 2, which is negative 1. Since there are negatives all over, I would multiply through by negative 1, and when multiplying through, the inequality sign has to reverse. So I will have negative 2 times negative 1, which is 2, should be greater than or equal to 3 all over 2 tan alpha, which in turn is greater than or equal to negative 1 times negative 1, which is 1. This again, I can switch, or rather I invert. If I'm inverting all through, remember my aim is to make tan alpha the subject, so I invert all sides of the inequality and reverse the signs. So if I begin to invert, I would have half is less than or equal to 2 tan alpha all over 3 less than or equal to the inverse of 1, which is still 1. Then what I will need to do now is to eliminate 2/3, and to eliminate 2/3 I simply multiply through by the inverse of 2/3. The inverse of 2/3 is 3 over 2, and so multiplying through by 3 over 2, I get 3 over 2 into half less than or equal to tan alpha, because 2/3 times 3 over 2 is 1, it was the inverse, less than or equal to 3 over 2 into 1. And finally I get that 3 all over 4 is less than or equal to tan alpha less than or equal to 3 over 2 as required. Now an alternative method would be to work with this in 2 parts. You first take this part and solve the inequality to have an expression for tan alpha, and after you take this other part, solve an inequality to have an expression for tan alpha, and then you conclude to arrive this one. That is another possibility, but I think this one is appropriate for the question. We are given that tan alpha is less than or equal to 1, and then asked to find E and hence the velocities of A and B after impact. Find E. So we had already an expression for E. E from this part, E is supposed to be 2 minus 3 all over tan alpha, and when tan alpha equals 1, because it's less than or equal to 1, so we take the case where it is 1, we have that E should be a constant. So whatever the value of tan alpha, it should always give you the constant E. So we take the case where tan alpha is 1. When tan alpha is 1, we have E is supposed to be 2 minus 3 all over 2 tan alpha, sorry. So we should have 2 minus 3 all over 2 into 1, which gives 2 minus 3 over 2, which is half. So E equals half. And now we are asked to find the velocities of, following this result, to find the velocities of A and B after impact. So VA and VB. Now VA is supposed to be X, the component, remember VA has two components, a component along the line of centers and a component perpendicular to the line of centers, while B has two components, a component along the line of centers and a component perpendicular to the line of centers, although it is 0 in that case. So I should be talking of VA being X times the unit vector in that direction plus 5 times the unit vector in that direction, and VB should be Y times the unit vector in that direction plus 0 times the unit vector in that direction. So we get that VA equals X times the unit vector along the line of centers. Don't forget it was the unit vector of vector A plus the component perpendicular to the line of centers times the unit vector in that direction, which was B cap. So from here we can see that when E equals half, remember X was supposed to be, we had X as 10 over 3 into 2 minus E. So X is 10 all over 3 into 2 minus E, and that gives 10 over 3 into 2 minus half. That will be 10 over 3 into 2 minus half gives 3 over 2, and that gives 5. X is 5. So we have that VA should be 5A cap plus 5B cap. That will be 5 into A cap was 5 into 3I plus 4J. Velocities, remember, have to be expressed in terms of I and J. So that's why we bring in the unit vectors and substitute now. Plus 5.1 over 5 into 4I minus 3J. That gives 5 will cancel 5. We are just left with 3I plus 4J. Plus 5 cancels 5. 4I minus 3J. We end up with 3 plus 4, which is 7I, 4 minus 3, which is 1J meter per second. That is the velocity of A after impact. Now velocity of B after impact should just be, remember B was stationary initially, so the component perpendicular to the line of centers is still 0, and so we just have Y A cap. The component that was parallel to the line of centers was Y, and Y gave, Y was 20 all over 3 into 10 plus, sorry, 20 all over 3 into, 1 plus E. So dot 1 all over 5 into the unit vector again in the direction of the line of centers, which is 3I plus 4J A cap. And so let us just continue this way. VB should be 20 over 3 into 1 plus half. E is half. Dot 1 over 5 into 3I plus 4J. and that gives 20 over 3 into 3 over 2. 1 plus half is 3 over 2, plus, not plus, should be dot, 1 over 5 into 3i plus 4j. 3 cancels 3, and then 2 cancels 20 to give, so 3 cancels 3, 2 cancels 20 to give 10. 10 divided by 5 is 2, so we have VB being 2 into 3i plus 4j, which is 6i plus 8j meter per second. So those are the velocities of sphere A after impact, being 7i plus j meter per second, and the velocity of sphere B, as I said, VB equals 6i plus 8j meter per second. Hello, in this session we look at this question of June 2017 of the Cameroon GC Board for the Mathematics paper 3. It has to do with oblique impact. The question says, show that the vectors A equal 3i plus 4j and B equals 4i minus 3j are perpendicular. A smooth sphere A of mass 2m moving on a smooth horizontal floor with velocity 10i plus 5j meter per second impinges obliquely on a smooth stationary sphere B of mass m. At the instant of collision, the line joining the centers of the spheres is parallel to the vector A. Given that the coefficient of restitution between the two spheres is E, and that the direction of motion of sphere A after impact makes an angle alpha with the line of centers of the spheres, show that A 4E, show that A 4 minus 2E times tan alpha equals 3 for 10 marks. B 3 over 4 is less than or equal to tan alpha less than or equal to 3 over 2 for 2 marks. C, given that tan alpha is less than or equal to 1, find E and hence find the velocity of A and B after impact. That part is for 5 marks.